All right, good morning, guys. I want to start off by talking about the calendar for our weeks leading up to Thanksgiving. So today we're going to start chapter 5, talking about derivative rules for natural log. You're going to see that this is going to feel a little bit like chapter 2. We're going to revisit a lot of things that we've seen in chapter 2, such as product rule, chain, quotient, implicit, but we're just doing it with a different set of derivative rules, but a lot of things will apply. We're also going to see a lot of things that are familiar, like curve sketching, first derivative tests, concavity. So in a sense, we're going to see a lot of review items are going to start popping up. And each time we come across a new type of function, we're going to go through the same process of learning how to do curve sketching or related rates, or so we kind of hit all the big topics for derivatives already. We're just now going to be applying them for different types of functions. On Monday, we will finish 5.1. We'll do a little curve sketching. On Tuesday, 5.3 and 5.4, I think, are relatively short in terms of the amount of content, so maybe we'll squeeze both into the same day. It's just that we want to be able to spend time practicing these concepts. So we'll spend Wednesday doing practice. Thursday, we'll learn another derivative rule. Friday, we'll practice those derivative rules. And then the week before Thanksgiving, we'll have 3 days of test review, Thursday test, and then Friday, we'll start our last section, which is just trig derivatives. We'll have maybe 3-4 days to continue reviewing trig derivatives the week after Thanksgiving, and we'll have a quiz after, one final quiz after the break. The second week of December, we will have a full week or close to a full week of review for your final exam. And then your final exam, fall exam, is going to be that third week of December. Okay. Now, talking about the final exam, still working on the format of that exam, but that, I believe the exam is going to be optional for all students. Okay, optional for all students. But I'm still going to encourage you guys to take it, because if it does help your grade, I'll enter it into the grade book. And also, but if it doesn't help your grade, then I'll just leave it out. Okay. And also, if it helps your grade, I'll also use it to replace your lowest assessment grade, whether it's your lowest quiz grade or lowest test grade, whichever helps more. So that's another benefit of taking it and putting effort into it. Okay, another incentive there. So yeah, so I think that kind of highlights the big points leading to the end of the semester. Any questions that you guys have right now?
Can I borrow you to Brian for a second?
Sure. And just like on these previous tests that you've had, open notes, calculator, bring your calculator. Okay, so, but I'll give you guys details about the format of the final exam. Probably after Thanksgiving break, I'll have a better idea what that will look like exactly. Okay, no questions so far? Okay. Okay, so let's jump into our notes for 5.1. If you guys can spend a minute to copy this down here. All right, so to intro log functions, they are going to be, log functions are inverse functions of exponential graphs. And we start off with natural log base E, because it's kind of the simplest, kind of like the parent graph. There's some nice features about base E that allows the graph to, or for the derivative to come out nice and clean. And we are going to talk about logs of other bases like base 2 or base 3, base 5, but they're all kind of built on top of this this function, this natural log. So that's why we start with this. And okay, so here are some features of the graph. First, there's a vertical asymptote at on the y-axis, so at x equals 0. There are two order pairs that are nice to know. One is that there's an x-intercept at 1, 0, and there's also another order pair at e, 1. So e is an irrational number, it's around 2.7. The graph is going to rise in this shape, kind of a half of a concave down graph. It doesn't decrease. It's going to keep increasing, but it's going to hold this shape. So domain is all positive real numbers. So anything to the right of 0, the graph is going to exist. There, the range, y values will extend from negative infinity to positive infinity. It's growing at a very slow rate, but it will work its way up to positive infinity. Graph characteristics, the graph is always always continuous within this domain, so there are no asymptotes that's going to break up the graph. Always increasing. And it's always concave down. Okay. So it's always going to hold this shape. Okay, there's a couple of things I want to point out to you about this graph that I find helpful or find useful. Okay, and it's the fact that, okay, same graph here. It's the fact that if we're looking at trying to figure out what value of natural log, like natural log of 1/2 or natural log of 2 or natural log of 3, I think many of us are just going to feel lost, right? Like I have no idea of knowing what that value is. I need a calculator, right? So I want to show you that if you can sketch this graph, and this is an easy graph, right? Asymptote, 2 simple order pairs, and then the graph's concave down going through those 2 points. That we can do a lot of approximations for values without the use of calculators. Now, maybe it's not as important this year because you're going to have access to calculator for everything, but usually on the AP exams, there are non-calculator and calculator sections. And then being able to know our way around certain things without a calculator is helpful. But I still want to kind of go over this with you. So looking at the graph, where is natural log of 1/2 going to land? Maybe we don't know the exact y value, but we know it's what? Negative, right? That's good enough for us to make have some ballpark values, right? We know it's somewhere here, right? Probably not too far down because it's still relatively close to 1, but it's going to be less than 0. Right? If you were to plug in the calculator, you'll get negative 0.7. Okay, but decimal is not that important. I want to just be able to have some idea of where these values are. Natural log of 2, okay, you may not know the exact y value, but we should be able to narrow down our options, right? Where's natural log of 2 going to be?
Between 1 and e.
Yeah. Okay, so good, between 1 and e. But what about the y value?
Just under 1.
Yeah, but positive, right? Greater than, so maybe 0.6, maybe 0.7. Okay. But we know e is 2.7, so we know it's going to be somewhere here, right? So you may not know what natural log of 2 is, but you know kind of ballpark value that's going to have to be between 0 and 1, probably somewhere like 0.6. Okay, how about natural log of 3?
Positive and after e.
Okay, after e. What about the y value, though? If it's sitting here, let's say, greater than 1, but not much greater than 1, right? Natural log rises at such a slow rate. It's greater than 1, but yeah, so it's probably like 1.7 or something. Yeah, oh, sorry, even less than that, 1.1. All right, so it's barely above 1. Okay, so just knowing some values. Now, other natural log values, we can expand, but basically just knowing this information is enough to find any log values, really. But just so that we don't feel so helpless and lost without a calculator, just by having this graph in front of us, we have some general idea where values are going to land. Okay, so let's look at example 1. Sketch the graph of natural log of x minus 3. Whatever makes the parentheses 0 is going to be where your vertical asymptote is. So your vertical asymptote is going to be by setting x minus 3 equal to 0. And if you know where your vertical asymptote is, you also know the starting point of your graph. So we know our graph is going to have this shape to the right of the asymptote, so we just sketch that graph to the right of the asymptote. So domain, it's going to be from the asymptote forward. Oops, sorry, not 0, 3. Example 2, draw the function natural log of x and answer the questions below regarding limits. So it says limit as x approaches 0 from the right side of 0. So if we're approaching 0 from the right side of 0, where's the y value headed towards?
Negative.
Negative, yeah. Okay, limit as x approaches 0 from the left side of 0. That means we need to start at a point to the left of 0. Undefined, right? We have no point to start with, so there's nothing to work from. So yeah, it doesn't exist. And in general, what needs to happen for our full limit to exist?
Continuity.
Not continuity, but what about the one-side limits?
Continuity.
Yeah, they have to approach the same y value, right? Or not only the same real number y value. So there's not even a real number here. So, and this doesn't even exist. So these aren't going to be in agreement. But if the left side and right side are both moving towards a whole, or 3 or 5 or a real number, then that's enough for a limit. But here, we don't have that. Okay, limit as x approaches infinity. This means that we are following the graph off the grid to the right. So if we follow the graph off the grid to the right, we follow the path of that arrow. That arrow is leading us towards y value, right? Keeps going up to positive infinity.
Mr. Q,
Yes, question?
how do you know what function to graph?
I'm sorry?
How do you know what function to graph?
Oh, it says natural log of x, so I'm just
Oh,
graphing
okay.
these. These are all natural log of x. Okay, some properties here. Natural log of 1 is 0. That's just an ordered pair on the graph. Natural log of e is equal to 1. That's an ordered pair on the graph. And then we have product property, quotient property, and power property. So I wrote it out in a different form here, just so it'll be easier to reference. So let me talk about these properties here. These properties will be helpful. We're going to practice expanding, condensing these, and then we're going to see how these play a role when we find the derivative. But ultimately, we're going to be able to apply these properties so that our derivative is easier. When we have a messy derivative problem, we can avoid quotient, chain, messy rules by expanding into easier parts so that we can take derivative of smaller problems rather than taking derivative of one messy large problem. So that's really the ultimate goal of these properties for us, at least from a calculus perspective. So here are the properties. If I have natural log of a times b, I can expand that into natural log of a plus natural log of b. If I have natural log of a over b, I can expand that into natural log of a minus natural log of b. If I have natural log of a to the n, I can bring that exponent down in front and make it n times natural log of a. Okay. As a side note, we don't have an expansion rule for natural log of a plus b. If you see natural log of a plus b, it's kind of stuck the way it is. We cannot distribute, quote unquote, distribute the natural log through. This is not a standalone term. The a plus b is inside the natural log. We can't say natural log of a plus natural log of b. Okay. And also this conflicts with this rule here. So it feels like we can come up with a new rule here, but this property doesn't exist. So if you see this, this kind of has to stay as it is. We can't go any further with this expression. So let's look at example 3. It says expand natural log of 3e squared. Do you see a property that we can use here? So yes, eventually we're going to be able to use power property, but I think there's a larger one that we can use, and that's the product one. Yeah. So how can I use the natural log of AB with this problem?
So ln3 plus ln e squared.
Good. Okay. Can't do much else with natural log of 3, but what can we do with natural log of e squared?
Power property.
Yeah, this exponent can freely come down, right? Okay. So there's something else we can do. Is there anything that we can do to clean this up? What's natural log of e? 1. Okay, right. Okay, any questions there? before we go to the next page, I want to link up what we're going to be seeing on the next page. So you can call this example 3B here. If I have a messier expression and I ask you to expand, I want to talk a little bit about a quick way to expand without having to go through a lot of steps. Okay. So let's say I have a kind of a rational expression within my natural log, and I ask to expand. We can expand using a combination of product and quotient property, but rather than having to write it out multiple times, here's a quick way that we can get to the fully expanded without having to do a lot of writing. So here's the general rule is that if your expression is part of the numerator, it's going to be a part of a positive natural log expression. If your term is in the denominator, it's going to be part of a negative natural log expression. So a quick way to allow us to expand without having to go through a lot of middle steps is see where it's located, and then just make it either a positive or negative natural log. So my 3 plus x is in the numerator, so I'm going to make it part of a positive natural log expression. 9 minus x is also in the numerator, so I can make it part of a positive natural log expression. X plus 1 is in the denominator, so it'll be part of a negative natural log expression. And x minus 1 is also in the denominator, so after all the middle steps are all done, it's going to end up being negative. So there's a quick way to expand without having to do a lot of writing. Okay, any questions here? Okay, so likewise, I can take an expanded form and condense it without having to go through a lot of steps either. So same rule applies. If I have a bunch of natural log terms and I'm trying to place them within one natural log expression, I just have to figure out where these expressions go. And they're either going to go in the numerator or denominator, and the way that we know is it part of a positive or is it part of a negative, right? If it's part of a positive expression, it's going to go up top. If it's part of a negative expression, it's going to go below. So 3 plus x is going to go above. 9 minus x is going to go above. X plus 1 is part of a negative natural log, so it'll go below. X minus 1 is also goes below. So we're back to where we started from, but it's nice to kind of practice going from one form to the next and going backwards. Okay, any questions there? Okay, so let's practice a condensing problem on the next page. We're going to try to go from here to here on the next page. Okay. Example 4, condense this expression. To help us see things a little bit better, if you guys can put a bracket with the 2 outside of it. And the first thing that we want to try to do is try to get those natural log terms down to one natural log term. So I know it's going to be natural log. I see a bunch of positive and negative, so I know I'm going to have to decide where they go, either above or below. And I'm just focused on the x plus 1, and the x minus 1. I just have to make sure I know where to put those. Okay, where does the x go? Okay. The x plus 1? Okay, part of a negative natural log, right? And the x minus 1?
No.
Yeah, the negative there tells us where to put it. Okay, if you want to FOIL this out, that's fine. But we still have a 2 sitting here. Now, a fully condensed expression has only one natural log, and also there's nothing in front of the natural log. So we need to put this 2 in another location. Exponent. So you can leave it in factored form, or you can expand this out. It doesn't matter. It's up to you. But the 2 has to come up. Okay, any questions? Okay. So let's move on to our new derivative rule. We have a rule for natural log functions. And the rule is this. The rule is that if I have natural log of u, and u is just going to be whatever is inside my natural log expression, I'm going to take the derivative of that expression and put it above, whatever that derivative is, and I'm going to divide it by the original expression inside that natural log term. So we don't need a lot of space for 5 and 6, so we can draw a line down. We're just going to use this. We'll save this for another problem. Okay. All right. So if I want to find, let's start with the easy one here, natural log of x. My u value is just this x inside the parentheses. So if I want to find the derivative, I'm just going to follow what the rule says. The rule says take the derivative of what's inside the parentheses, and that's going to go above. So what's x's derivative? 1. Divided by the original value, just x. Yeah, that's it. Y prime equals 1 over x. Notice that when you find the derivative, there's no more, we don't write natural log again, right? Natural log just drops out from our, doesn't appear in our derivative rule. Okay, questions there? Okay, if I have natural log of x squared minus 5, this is my u value. So I want u prime over u. Okay, so u prime is going to be the derivative of the x squared minus 5, which is what? 2x. 2x, right? The 5 goes away, goes to 0, right? Divided by the u value.
X squared.
Yeah, don't change it, right? Just copy exactly as you see it. Okay, questions there? All right, a couple of things I want to bring up. Make sure that we don't cancel the x's, right? There's a minus. If we cancel this out, we're changing the expression. Right? Can't cancel across addition or subtraction. And the second thing is, okay, we're learning these new derivative rules, but it does the same thing as other derivatives. Okay? All it does is describing the steepness of any point on this original graph. So if I plug in, let's say I plug in 2, and I get 4 over -1, -4. So that tells me that at 2, the graph, this graph is going to have a slope of -4. It's going to be rather steep. All right, so it does the same thing as other derivatives. It just describes the slope of the original graph. All right, questions so far? Okay, now look at example 7. It looks increasingly difficult, but here's the good thing. The good thing is that when you're dealing with a natural log or log expression and something looks messy, we can always simplify. We can always expand. And if we expand far enough, we should have a relatively easy derivative rule, which is kind of breaking a large problem into smaller parts and then just handling each separately, basically. So we're going to always expand first. So if you're having to go through a really difficult time with your derivative with natural log, you probably should have expanded first. Okay, so here are our properties. Do you see an obvious one that we can start with first?
So quotient.
Yeah, I see the quotient. Maybe there's product and power involved here, but I'm going to handle the most obvious ones first. All right, so I see a numerator denominator. So I'm going to treat the x squared as my a. I'll treat the square root as my b. And I'm just going to write it as 2 natural log expressions. Okay, so we're making some progress, right? We have these already look easier than what we started with, but we're going to keep going, okay? what can we do with this second expression? Is there anything that we can do to rewrite it, make it easier to look at?
1/2 ln 2x cubed.
Yes, but I'm going to back up a little bit. I'm just going to rewrite the square root as an exponent. But yeah, you're right. Oops, sorry, minus. So anytime I see a radical, I want to rewrite it as rational exponent. It helps me see things a little bit better. And then I see, okay, I have some exponents I can bring down, right? I can bring the 2 down in front. I can bring the 1/2 down in front. Okay. So now if you look, these u values are now a lot easier to manage, right? U prime over u is not going to be anything that is that's not going to be a multi-step problem. We don't have to go through any messy rules. Okay, so this is a good place for us to begin our derivative step. Any questions here? I think sometimes, well, students have asked in the past, well, can I expand this further, right? Why can't we expand the 2x cubed even more? And the answer is yes, we can expand it further if we want. But I think it comes to a point where if the derivative feels easy enough to apply, just go ahead and apply the derivative. Sometimes it's not worth the effort to expand all the way, because if you expand all the way, you got to write out a lot more terms, and it's just not worth the effort sometimes to write out so many terms when the derivative is already relatively easy. So I think that's kind of a judgment call on your part, where you can expand all the way if you want, but after doing enough problems, I think you're going to see that it's probably not worth the effort, or you can be able to begin to recognize when to stop or when to continue. Okay, so now let's find the derivative, y prime. So technically, I could have stopped here and just done 2x over x squared. Then that's fine, because that's easy, but you can also bring it down. So I think this is kind of like, it's up to you, right? Maybe you have one preference over the other, but either form is good. But I wouldn't go past this one. I don't think it's worth the effort to expand this past what we have here. Okay, so derivative 2 stays. What's natural log of x's derivative? 1 over x. 1/2 is the coefficient, that stays. Okay, u prime over u.
6x.
6x squared over 2x cubed, yeah. Clean up where I can, not much here, but I can take out the x, I can reduce some of these coefficients here. I'm not going to ask you to find common denominator. If you can reduce your fraction relatively well, then that's good enough. Okay, any questions here? All right, if you guys can use the space above, we'll call this example 8. And we're going to do an implicit differentiation problem here. And that means we got to find dy dx. We know we have to do implicit whenever your equation has y's that look out of place or multiple instances of y's. Okay, so here's the problem. So we have y's kind of scattered through the equation. We know we have a couple of dy dx's that we're expecting along the way. Right. But I just want us to make some observations to begin with. We're going to find the derivative down the road, but what's involved here?
Power rule, or product rule.
Yeah, power rule, but also product rule, right? See, 4x and y are obviously two separate expressions. We can't just do 4 times dy dx, right? There's more than that, right? We got to go through product rule. Okay, so I'll make a note of that. We know we got to do product rule here. All right, here I have natural log of x squared y. This looks like a messy natural log expression. We do eventually want to find the derivative, but what do you think we can do first? Yeah, let's take here. Anytime you see natural log, you always want to see if I can take advantage of expansion properties. Just makes life easier in terms of derivative. So I'm going to rewrite the 4xy. I'm not going to do the derivative just yet. And I'm going to work on my expansion. Okay. How can I expand the natural log of x squared y?
ln x squared plus ln 1.
Okay. Okay. You can leave the 2 up or bring the 2 down. Okay, if you want to bring it down, that's fine. Doesn't make the problem that much easier or harder. Okay, so now I think we're at a good place, right, where the derivative is manageable with natural log. Okay, we can't work our way around the product rule, so we got to do product rule here. But here, at least we've cleaned it up where it's a lot easier now. Okay, so product rule. Okay, let's go through this term by term here. 4x becomes 4. G function, no changes. F function, no changes. Okay, G prime. 1. What else? Okay, we just took y's derivative, so we also need dy dx, yeah. Okay, so all this is for my 4xy. Okay, let's continue. 2 natural log of x. What's 2 natural log of x's derivative?
1 over, or 2 over x.
Good, yeah. So I have 2 minus my coefficient. I have the 1 over x that represents natural log of x. Okay. Plus natural log of y. We can also apply rule here, right? U prime over u. What's u prime over u for natural log of y? 1 over y. But we just took y's derivative, so we also need what? dy dx. Equals 0. Good. Right. The 7 is also being impacted by the derivative. So constant goes to 0. Okay, the rest is cleanup. The rest is just solving for dy dx, but I want us to look at this again. Any questions up to this point? Okay, so this is a lot, right? I mean, we did power rule, we did product rule, we did implicit, we did log expansion. All this is kind of all contained within this problem. But we're taking chapter 2 and we're just kind of piling on more things on top of it, right? Okay, so here's our cleanup. I'm going to isolate these terms on the left. I'll factor out the dy dx. Distribute or divide the parentheses over. So this looks like a messier derivative rule, but it does the same purpose as other derivatives, right? All this is doing is if I give it an order pair, it'll give me a number, and that number is going to tell me how steep a point is on this original graph, whatever this graph looks like. Okay, questions? I want us to go to the classwork page, but I think I want to show, I think going through some of these problems with previous periods made me realize I think it's good to see how parentheses can really impact how we do expansion properties. And some of these they look so similar, so subtle. I think it's good to kind of line them up next to each other so you kind of begin to see and recognize those really small but important differences. So I'm going to have you guys put this on a separate sheet, maybe, and I want us to explore, these three different types. I just kind of began to see that pattern as I was going through these problems with the previous periods. So I want us to explore this one here. Y is equal to natural log of x cubed versus natural log of x. Sorry, I'm going to give myself more room here. Okay, let me talk about expansion for each of these. They all kind of look like kind of similar, right? It's really just the parentheses that kind of separating everything, but it has a huge impact on what we can do and what we can't do. So, okay, so the implied parentheses is here. Okay, we can leave it out, but just for comparison purposes. Now, can we expand this? Yes, that 3 can come down. Okay, and then if you want to find a derivative, you go to the derivative. Okay, can we expand this?
No.
Okay, what is it about this that's different than this?
Because cube isn't connected to just x.
Right, if we can only apply product property if the exponent only sees that specific value inside natural log. This is a different thing, right? The exponent is seeing more than just the x, seeing the entire function. So if I want to find the derivative, hold on, let me just finish this problem here. Y prime would be equal to 3 times 1 over x, which is 3 over x. Okay, if I want to find the derivative, I can't do any expansion, which forces me to leave it in this form. And if it stays in this form, I have to go through what?
Chain.
I gotta go through chain rule. Yeah, there's no way around this one here, chain rule. So chain rule is outside versus inside and taking each derivative separately. So y prime. What's outside's derivative?
3 squared.
3 parentheses squared. Bring down the original natural inside function, no changes, times
1 over x.
times 1 over x. Okay, you can leave it in this form, or I'm just going to clean up a little further. All right, so that's one distinction. Moving on to this one here, can I expand this?
Yeah.
But can I bring the 2 down as it is? Can I bring that 2 down?
No,
Okay, why not?
because you have a coefficient.
Yeah, that coefficient prevents us from being able to expand. I mean, we can expand it, but not power first. What do we have to? I mean, I would say if you're seeing this problem, I wouldn't expand any further because it's easy derivative rule. But if you want to expand, what do you have to do first? I got to separate the 3 from the x squared before that 2 can come down. I can't just bring that 2 down in front. I got to make it y is equal to natural log of 3 plus natural log of x squared. And then if you want to bring that 2 down, then you can bring it down. And then y prime will just be 0 plus 2 over x. Okay. But my suggestion is if your u value is already sitting at a pretty easy form, I would jump into the derivative. I don't think it's worth the effort to expand to that point. It's not wrong. It's just just time saving purposes. Okay. Last one here. Can I expand this one?
Yes.
Yes. The 2 can come down because the 2 sees both the 3 and the x. So this falls into that category. The 2 can't come down here, but this one you can. So there's 4 problems here. They all look similar, but then we approach all of them differently, right? So I think it's worth the time to look at these, study these, and kind of hopefully gain a stronger sense of how to work expansion properties. Okay, so if I want to find the derivative of this, I can say y prime is equal to 2 times u prime over u, so that's 3 over 3x. Okay. The homework that I have for you is on this worksheet, second page, 51 to 59 odd. Okay, just so that you guys get some more practice, but hopefully you guys are getting there where you feel comfortable. Okay. We'll review a little bit more on Monday. We will start we'll finish 5.1. We can start 5.3. We'll do some curve sketching. Okay, if you're on Teams, hope you guys have a good weekend. See you guys Monday.